Welcome to OOTO TV, the out-of-the-office investigation from the past into the future of marine navigation and autopilot technology. Hello and welcome. This time we're discussing the requirements specification for marine navigation and piloting tool for both inshore and offshore global navigation. Now that's a mouthful, but it really gets to the heart of maritime safety and efficiency.
I'm Lieutenant Colonel Collingswood.
And I'm Major Sergeant Cormule. In this investigation, we're really going to get into the incredible journey we've taken, from the very tactile world of paper charts and parallel rulers to these amazingly sophisticated data-driven digital systems you'll find on the bridge of pretty much every modern ship. Yep, we'll be looking at the fundamental design principles that hold these critical tools together, the incredible tech leaps that even made them possible, and maybe the most important part, that complex, always-changing relationship between the mariner and the machine. And, we'll also try to peer over the horizon a little, see what the future holds, because these relentless advances in connectivity and data are promising to reshape the art and science of navigation, yet again. So let's get started.
Cormo, this quote, it really cuts right to the heart of what we're talking about. This isn't just some abstract tech discussion about lines on a screen or crunching data points.
It's not at all, Collingswood. That's exactly it. Behind every single waypoint, every automated course correction, there's this fundamental promise of safety and, well, getting the job done. The stakes are just incredibly high. For the captain of that dive boat, it's about putting those divers in the exact right spot over a reef, and more importantly, being right there to pick them up safely when they surface. For the pilot of a supertanker, we're talking about guiding 250,000 tons of oil through a narrow channel without causing an environmental catastrophe. The navigation system isn't just a tool, it's the very instrument a captain uses to execute their judgment and responsibility. It's a direct, critical link between the technology and the trust people put in you.
So, to give you a roadmap of how we're going to tackle this, we'll kick things off by looking at that huge shift from paper to pixels in what we're calling the modern mariner's compass. After that, we'll lay out the core principles of system design with what we're calling the 3 pillars. Then, we're going to trace the fascinating tech evolution that got us to where we are today from radio waves to satellites. From there, we'll get into the crucial and, let's be honest, often contentious user experience in the human-machine interface. And to wrap it all up, we'll explore some of the exciting and challenging developments on the horizon in connecting to the future.
All right, let's get right into our first section. Look, there's absolutely no denying that modern systems like ECDIS, that's the Electronic Chart Display and Information System, are completely indispensable on a modern bridge. They've totally revolutionized the navigator's job. But, and I think this is so important to say right up front, the old ways still hold immense value. Paper charts and the deep-seated skills to use them, celestial navigation, dead reckoning, they have to remain a vital reserve, a fallback for when those pixels inevitably go dark. We've seen it happen. There have been incidents where GPS blackouts or total system failures have left crews dangerously disoriented, all because those fundamental skills were allowed to wither away. It's a critical vulnerability we just can't afford.
In this right here, this slide frames the fundamental problem these systems are all trying to solve. You see, the bridge of a ship isn't some quiet office. It's an incredibly dynamic and often intensely high-stress environment. Just picture a port arrival. You're managing engine orders, you're on the VHF radio with tugs and the pilot, you're monitoring traffic all around you, all while guiding a vessel worth hundreds of millions of dollars down a narrow channel. That's what high workload really means. Fatigue? Well, that's a constant companion on long voyages. And ambiguity is everywhere. Is that faint blip on the radar a small fishing boat, or is it just sea clutter? And in the middle of all those distractions, a critical decision has to be made in a split second. This is the crucible where navigation technology is truly tested.
And this is exactly where the advantages of a system like ECADS just pop. The improvement is absolutely massive. With the old traditional charts, a navigator spent hours, literally hours, hunched over a chart table with parallel rulers and dividers, physically plotting points, calculating course corrections for wind and current. It was a true skill, no doubt, but it was so meticulous, so slow, and dangerously prone to simple human error.
Oh, a slip of the pencil, a simple math mistake, that could have catastrophic consequences.
Exactly. Now, with ECADS, huge chunks of that planning process are automated. The system is just this powerhouse, integrating real-time data from every key sensor, your GPS position, your depth sounder, your speed log, all onto one dynamic, layered display. It's not just a static map anymore. It's a living, breathing picture of your vessel's situation. And it even comes with look-ahead functions and early warning alarms for things like approaching shallow water or straying from your planned track. It's a whole new world. Okay, so we've established the need and the basic advantages. But how do you actually go about building one of these systems that can be trusted with lives, with cargo, with the environment? It's so much more complex than just writing some clever code and slapping it on a screen. It requires a really robust, disciplined framework. And that brings us to what we're calling the 3 essential pillars of designing any effective navigation tool.
And that really is the million-dollar question, isn't it? What are the key elements? To create a tool that isn't just functional, but is also reliable, safe, and truly useful for every single phase of a voyage, the requirements have to be meticulously defined. You just can't leave anything to chance. The whole thing has to be broken down, step by step, into 3 distinct but deeply interconnected categories. And let me tell you, getting this initial specification right is what separates a world-class life-saving system from a dangerous and very expensive liability.
And here they are, those 3 pillars. First, and I would argue most importantly, you have to understand your audience needs. The requirement specification for marine navigation and piloting tool for both inshore and offshore global navigation will vary dramatically. It all depends on the region, the size and type of vessel, and even local laws and traditions. The pilot of a high-speed ferry has completely different needs than the master of a slow-moving bulk carrier. Then you've got the technical requirements. This is the real nuts and bolts of it. What data does this system need to pull in? How does it process all of it? What are the standards for how it communicates with all the other equipment on the bridge? And finally, and this one is absolutely non-negotiable, you have safety, regulations, and restrictions. Marine navigation is a world governed by international bodies like the IMO, through big conventions like SOLAS, not to mention all the national and local authorities. Your system must comply with every single one of them, no exceptions. These 3 pillars, they form the absolute bedrock of the entire design process.
Collingswood, you're listening to OTO TV with research by author Paul Bulow. Okay, so let's dig a little deeper into those technical requirements because this is where the system really comes to life. A core part of the requirement specification for marine navigation and piloting tool for both inshore and offshore global navigation is that it absolutely must incorporate existing databases of charts and maps. But, and this is the critical part, it has to update those maps and the ship's plotted course in real time. And it pulls this off by taking in a constant stream of data from the vessel's own sensors. It needs GPS for position, the echo sounder for depth under the keel, the Doppler log to know its speed through the water versus over the ground, which is crucial for calculating currents, by the way. It needs the gyro for a stable heading, and then it synthesizes all of this with the planned route and external data, like weather forecasts and AIS traffic info, to calculate vital outputs like your estimated time of arrival and your fuel consumption.
So, you might be wondering, how do all these different pieces of equipment, which are often made by totally different companies, talk to each other reliably? Well, that's where a standard like NMEA 0183 comes in. The easiest way to think of it is as a universal language, a kind of digital Esperanto for marine electronics. It defines a standard format for these little data sentences. So, for example, the sentence that starts with $VDVW communicates the vessel speed. The one that starts with $VDDPT gives the depth. It's this common language that allows the ECDS to understand what the depth sounder and the GPS are telling it. And you can see that tiny little field at the very end, *CC. That stands for checksum. It might look like a tiny technical detail, but its importance for safety just cannot be overstated. The Coromel is a simple but frankly brilliant form of data integrity check. Imagine it like this. You're mailing a package, and you know there are 72 items inside. So you write 72 on the outside of the box. When it arrives, the person on the other end counts the items. If there are 72, they know nothing got lost. The checksum works on a very similar principle, but with math. The sending device does a specific calculation, an 8-bit exclusive OR on all the characters in that data sentence. The result of that math is the checksum. The receiving device does the exact same calculation. If its result matches the checksum it received, it knows the data is intact. If they don't match, it means the data got corrupted somewhere along the line, maybe by some electrical interference, and the system knows to reject that piece of information. This tiny feature prevents a navigator from making a life-or-death decision based on bad data. It's a fundamental digital failsafe.
Okay, let's zoom out a bit. All this data integration is absolutely amazing, but the most fundamental piece of information any navigator needs is simply, where am I right now? And the technology we use to answer that simple question has gone through a staggering evolution. I mean, we've gone from relying on ground-based radio waves to a global constellation of satellites, and that single leap has changed absolutely everything about navigation.
Yeah, before GPS was everywhere, systems like LORAN-C were the absolute state-of-the-art. It was a terrestrial, ground wave-based system. You had these chains of powerful transmitters on land sending out precisely timed radio pulses. And the receiver on the ship would measure the tiny time difference in their arrival to calculate a line of position.
But it definitely had its limitations, right?
Oh, big ones. Its accuracy was hugely affected by the signal's path. Radio waves travel differently over land than they do over seawater, so navigators had to apply these really complex corrections called ASF, or additional secondary phase factors. These could even change with the seasons. And as you can see from the map, the coverage was regional at best. Look, it was a brilliant system for its time, and it took immense skill to use it well. But the jump to a truly global, all-weather, space-based system like GPS was a complete and total game changer.
It really was. And of course, we didn't just stop at standard GPS. We had to make it even better with differential GPS, or DGPS. It's such a clever way to defeat the system's own built-in errors. You see, even GPS has tiny inaccuracies, caused by things like satellite clock drift or atmospheric delays. So DGPS fixes this by placing a GPS receiver at a fixed, precisely surveyed location on the ground. This reference station is constantly calculating the difference between its known position and the position it's calculating from the satellites. That tiny difference is the error. The station then broadcasts this correction data out to any DGPS-enabled receivers on ships in the area. They apply that correction to their own calculations, and boom, it dramatically improves their positional accuracy, often down to a single meter or even less. It's fantastic.
And this slide just illustrates the practical application so well. This isn't just a theory, this is critical safety infrastructure. What you're looking at is the network of DGPS reference stations that provide coverage for the UK coastline. For a ship navigating the incredibly busy Dover Strait, or a ferry trying to dock in a tight harbor, or an offshore vessel trying to hold its position right next to a wind turbine, that level of enhanced accuracy isn't a luxury, it's absolutely essential for safe operations. It's what transforms GPS from a good open ocean tool into a precision instrument for the most demanding parts of any voyage.
Okay, so we've talked about the data, the sensors, the positioning technology. But none of that matters one bit if the human navigator on the bridge can't use it effectively, can't use it efficiently, and can't use it under pressure. And this brings us to what I believe is the most critical junction in the entire system, the human-machine interface. This is where all that complex technology has to be translated into clear, unambiguous, actionable information. The best system in the world is useless or, even actively dangerous if the interface is confusing or just poorly designed.
That's the key question, Coromio. So how can these systems provide a high-quality experience for the user? Well, a high-quality experience is one that actively reduces the user's workload, one that measurably increases their situational awareness, and ultimately one that inspires confidence in the system. Modern eCondis tries to get there through highly customizable displays. The navigator can declutter the screen for open ocean sailing, or add dense layers of information like traffic and depth contours during a port approach. They have these sophisticated route planning tools that don't just show you where you are, but constantly project where you're going to be in the next 5, 10, 30 minutes and warn you of dangers on that predicted path. The whole goal is to make the system feel like a powerful, intuitive partner, not some complex puzzle you have to fight with.
And for me, it's an absolute miracle. It has delivered unprecedented efficiency in voyage planning. The automated warnings for grounding risks, the ability to set your own dynamic safety contours around your ship, these features have, without a doubt, saved ships, cargoes, and lives. And from an operational standpoint, the fuel savings for more efficient routing have led to huge cost reductions across the entire industry. It is a revolutionary step forward, period.
I don't disagree with the benefits, Collingswood, but miracle is a very strong word. I see it as more of a double-edged sword. There is a real and a very present danger of over-reliance, especially among younger navigators who just trust the screen implicitly. And on the flip side, I've seen some older, more dismissive captains who neglect to learn the system properly, and they create a whole different set of dangers. And we can't forget the simple risk of garbage in, garbage out. The grounding of the cruise ship Royal Majesty off Nantucket was caused by something as simple as a GPS antenna cable coming loose, but the crew continued to trust the wrong position on their screen for hours. That's the menace side of the equation.
Cormiol, and this really gets to my biggest concern, the very real and dangerous phenomenon of alarm deafness. Look, early warning systems are fantastic in theory, but a warning is absolutely worthless if it doesn't prompt action. On many ships, if the alarms aren't configured properly, they can be going off constantly for minor, insignificant deviations. They just become routine background noise. The watchkeeper becomes desensitized through what we call alert fatigue. And a ship with a navigator who has become deaf to the warnings from their primary tool is, as the quote says, effectively blind. They are sailing with a completely false sense of security, totally unaware that a disaster may be just minutes away. This human factor is the system's greatest vulnerability.
That's a powerful point, Coramiel, and it really does highlight the absolute need for continuous, high-quality training. But if we look ahead, the evolution of these systems is far from over. I believe the next great leap forward is going to be driven by connectivity. We are rapidly moving from systems that rely mainly on onboard sensors and charts that are updated, every so often, to systems that are constantly connected to a global information network, pulling in a torrent of real-time data.
And this is the exact forward-looking question we need to be asking right now. Can we connect to both Starlink-type satellite systems and use library data to relay time-updated new geographic region and new weather data? The potential is there to not just get a weather forecast file once a day, but to have a constantly updated, high-resolution overlay of weather and sea state data right on the chart.
Exactly. Can we get instantaneous chart corrections for a new geographic region pushed directly to the ship the very moment they are issued by the Hydrographic Office, instead of waiting for a quarterly DVD to show up in port? This level of connectivity could fundamentally change the whole nature of passage planning and real-time situational awareness.
Collingswood, you're listening to OOTOTV with research by author Paul Bulow. The possibilities that flow from that kind of constant connectivity are just incredible. Imagine dynamic route optimization, where the system is constantly recalculating the safest and most fuel-efficient route based not on a forecast but on live weather, live currents, and even developing maritime traffic patterns pulled from an enhanced AIS network. We could have instantaneous over-the-air chart and software updates which would completely eliminate the old cumbersome manual process. And think about support. If a system has a glitch in the middle of the ocean, a technician ashore could log in, run remote diagnostics, and potentially fix the problem in real time. This constant high-speed data flow would transform the bridge from a self-contained unit into a fully integrated node in a global maritime information network. It's a huge step towards smarter, safer, and more efficient shipping.
But let's bring this all back to our central theme. As exciting as all this new technology is, it just underscores a fundamental truth. The requirements specification for marine navigation and piloting tool for both inshore and offshore global navigation is not a static document that you write once and then put on a shelf. It has to be a living process. These requirements are not static. They must be updated and evaluated on an ongoing basis. As new technologies like Starlink become available, the technical requirements have to adapt. As we learn more from incidents about the human-machine interface, our understanding of audience needs has to evolve. It's a continuous cycle of improvement, learning, and adaptation.
And that really leaves us with this final, and I think pretty provocative thought. We've traced the journey from paper to pixels, from radio waves to satellites. We've seen how these systems are built on pillars of user needs, technical specs, and regulations. But as these systems become more and more powerful, more accurate, and more automated, what happens to the role of the human navigator? Does their judgment, their experience, their seamanship, what we call the human element, does that become the ultimate backstop, the strongest link in the chain that ensures safety when the technology fails or presents a completely unexpected situation? Is the skilled mariner the ultimate fail-safe?
Or does that same human element, with its built-in potential for fatigue, distraction, complacency, and that over-reliance we've been talking about, does it become the most vulnerable point, the weakest link in the chain in an otherwise highly reliable technological system? There is no easy answer to that, but it is the central question we absolutely must continue to ask as we navigate the future. Thanks for joining us for this investigation from OOTO TV.